All right, so that's all the subatomic molecules. We've got protons, neutrons, electrons. Protons have 1 unit of positive charge. Neutrons have 0 charge. Electrons have 1 unit of negative charge. Protons and neutrons each have 1 atomic mass unit of mass. Electrons effectively have no mass. And then we have elements that are all unique atoms with certain chemical properties ascribed to them. All elements of a certain type will have the same number of protons, but they may have different neutrons or electrons. We can take those atoms and put them together to start forming molecules. So molecules are just 2 or more atoms that are bonded together. These are molecules. Whether you've got this molecule that's something, and I don't know what it is. I just randomly wrote molecule into Google, and that's what popped up. It's carbon and hydrogen at something. Yeah, thanks. Because it has hydrogen and carbon. Well done. This is oxygen, O3, so this is ozone. If you ever wanted to know what the ozone layer is made of, it's that. Those are molecules. There are, in the class of molecules, a Venn diagram of it. Here's a Venn diagram. If we were to have the whole big class is called molecule, a component of that is going to be considered the compounds. All compounds are molecules, but not all molecules are compounds. Compounds are substances that are made up of 2 or more elements, atoms of 2 or more elements. So for instance, water is a compound because it's made of oxygen and hydrogen. Carbon dioxide is a compound. It's made up of carbon and oxygen. Ozone is not a compound. It's just made up of a bunch of oxygen. Does that make sense? O2, oxygen, is not a compound, but it is still a molecule. So we've got to figure out ways to get these individual atoms to bind together, and that's tricky. Before we do that, let's talk about how we can simplify talking about molecules. Because nobody wants to draw molecules all day long. Nobody wants to build 3-dimensional representation. You might want to, I don't know. But you don't want to spend your time doing all of this. So instead, we tend to write out the molecular formula. Instead of drawing it out like, let's see if I can draw this one. That one's too much to draw. Instead of drawing H, and O like that, it's much more efficient to just write H2O. And assume they're connected where they're supposed to be. Well, you'll be able to tell that based on if the formula is written properly based on the formula. So here we've got C6H12O6. This is glucose. Super important for biology. You don't need to know it now, but trust me, by the next exam, should be the next exam, if not the exam after that, you will know this molecule backwards and forwards, how it's broken down and how it's built up. C6H12O6? It's glucose. It breaks down into ethanol. Yeah, you can break it down into ethanol. So you see these, that's the atomic symbol, carbon, hydrogen, oxygen. And the number next to it is the number of that particular atom in that molecule. The place people get confused is you have C6H12O6, and you might have something over here that says C612. Don't get confused between the atomic symbol and a molecular formula. This is saying there's 6 protons in carbon. This is saying there's 6 carbon atoms in this molecule. It's all about context. Get rid of that because it won't be necessary on the next slide. So, do a quick exercise. O2, how many oxygen are there? H2O, how many hydrogen? How many oxygen? Good. And I didn't even have to tell you that. If it doesn't have a number next to it, it means 1. C6H12O6, how many hydrogen? How many carbon? H2, how many hydrogen? H2O2, how many oxygen? So far, so good. Any questions? At this point, we're probably like 4 or 5 weeks into the high school chemistry course. There's a difference between molecular formulas and empirical formulas. And you know what? Never mind, I'm going to take this slide off. I don't like this. So there's a difference, and the deal is we really don't use them much in biology. It was in your book, so I was like, I'll put it on there. And I was like, we don't use it in biology. There's a difference between H2O2 and HO. The molecular formula is H2O2. The empirical formula is simply the simplified form of it. Yeah, it's not even just take the numbers out. It's keep the ratios, reduce it to its lowest form. It's not really necessary to know. Does lead to a good joke, though. H2O2. You guys know that's hydrogen peroxide. Hydrogen peroxide is what's called a free radical. It will wreak absolute havoc in bacterial cells, yet your cells are fine. Obviously, you shouldn't drink hydrogen peroxide. It's not good for you. And thus the joke. Two guys walk into a tavern. In this tavern, they're both very thirsty. One of them sits down and says, I'd like some water. Bartender, get me a glass of H2O. Bartender brings it out, sets it in front of him. He drinks it. He is so thankful. Next man says, that looks great. Bartender, I'll have a glass of H2O too. That guy died. Yeah, I know. There are 3 big types of chemical bonds between and within molecules that we're looking at. Ionic bonds, covalent bonds, and hydrogen bonds. Ionic bonds happen when an atom is going to release or gain an electron from a neighbor. Covalent bonds share some electrons. And hydrogen bonds are going to interact with electrons in another molecule. They tend to be intermolecular forces more than intra within a molecule. As far as strength goes, covalent's the strongest, ionic's next, and then hydrogen's the weakest. We're going to go through each of those on their own. And yes, you need to know these. Atoms want to be stable as much as an atom can want anything. Stability is what they crave. They want to be at that lowest energy level and remain sort of content and not change, and they're not malleable. It's just like you guys, for the most part, most people are looking for that stable relationship, right? You don't want to be in that one that you've been in, the one where the other person's absolutely insane. You've had those relationships. They're not the best. Well, they're fun at first, and then it's all downhill. You want that stable relationship, the one that's going to last. In order for an atom to be stable, it needs to have 8 electrons in its valence shell. Again, what's the difference between the valence shell and the other shells? It's on the outside. We're not there yet. So we've got these. They one have 8. That's called the octet rule. Carbon and oxygen each want 8 in their outer shell. So here we've got oxygen normally has 1, 2, 3, 4, 5, 6 in its outer shell. Here, 1, 2, 3, 4, 5, 6. Carbon has 4. So when you put them together and they bond, carbon is sharing 2 electrons here with 2 electrons from oxygen, giving you 8 surrounding oxygen, 8 surrounding carbon, and 8 surrounding this oxygen. So that's why they're that's when they're the most stable. They do this when their their valence shell is not completely filled. So most atoms are going to have 8 valence electrons in their outer shell, except for 2. These exceptions are important to know. Hydrogen and helium are both stable with 2 electrons in their outer shell. Everybody else, they want 8. So far, so good? So here we've got 2 molecules bound together. One has 7 electrons in its valence shell. The other has 7 electrons in its valence shell. How many do each need to finish? They need 8, so they need one more. So they can share a single pair. Now the periodic table will tell you how many electrons are in the valence shell of any given element, any given atom. You can count the number of columns to tell you that, as long as you ignore this entire section right here. And you know what? You can do that because we're biologists. So who cares about this? Not us. We only care really about 1, 2, 3, 4, 5, 6, 7, 8. Over here, they have 1 electron in their valence shell. They need then, for the most part, except for hydrogen, how many more? 7. Except for hydrogen, how many does hydrogen need? 1 more. Over here, on this side, how many do they have in their outer shell? 8. How many more do they need? None. They don't react at all. They're called the noble gases. If you want to store a document forever, put it in a noble gas because they're non-reactive, in case that's something you want to do. The Constitution is surrounded by, I believe it's argon, but I may be mistaken. I thought it was argon. They may change it out to either krypton or neon. So argon. But the idea is you surround it in this non-reactive element, and the paper doesn't break down anymore. Now, oxygen is extremely reactive. How many electrons are in oxygen's valence shell? 6. It needs 2 more. It will react. It's like the element that gets around the most. It is sharing electrons like crazy. And when it does that, it actually snags some electrons too. It breaks things down. So we know how many shells does iodine have. We talked about this. How many shells? 5. How many electrons are in its valence shell? 7. How many more does it need? 1. Yes? How do you figure out the number of shells? Right. How do you get the number of electrons? Yeah. You count over 1, 2, 3, 4, 5, 6, 7, 8. I really like being able to draw on this. This is just something I'm new to. It's fun. I tried to do it on this other thing I had before. It was a projected screen. It was a bad idea. And then I blamed somebody else. So, and of course I just recorded that, so that'll be fun. Let me see. Oh, so if we were to draw out a molecule of, say, oxygen. Oxygen has a grand total of how many protons? Yes. 8 is the correct answer. Well done. We have 8 electrons. We have oxygen. In the first shell, 2 electrons will fit. In the second shell, how many electrons are left? 6. 1, 2, 3, 4, 5, 6. So I spread them out, yeah. So I have a space here and a space there for an electron. It can bind to other molecules there. Does that make sense? So we could draw this all out. Over here, we have chlorine. I know this is chlorine because I could count the electrons in the shell and assume it's a neutral atom, or because I wrote the PowerPoint and I know I put chlorine there. So that's chlorine. How many electrons are in its valence shell? 1, 2, 3, 4, 5, 6, 7. Good. How many does it need? 1. It needs a total of 8, you're right. So thus it needs 1 more. Hydrogen, how many electrons does it have? 1. How many until it's stable? 1 more to make a total of 2, because hydrogen's the exception to our rule. The first shell only takes 2. So this, if we brought these 2 together, they could share those 2 electrons, leading to hydrochloric acid, HCl. HCl is some pretty, it's not terribly dangerous unless it's in high concentration, but it's an acid. And we're going to talk about how they break down in the next few minutes. That is termed a single bond. And if you look, we don't have to draw this whole thing out. We could just put an H with a single bar to the Cl. That means they're sharing one pair of electrons, or 2 electrons. Different numbers of electrons being shared lead to different strength bonds. Single bond, pretty weak. I mean, for covalent bonds, they're pretty weak. It's just a single pair of electrons being shared. Here, Gabby, hold this. Okay, don't let go. Okay. Don't let go. Okay. All right, so I can move around a whole bunch, right? Lots of flexibility, and I'm pretty distant. That would be a single. Okay, now you can let go. Single bond. Now, we could share 2 pairs of electrons. That makes a double bond. Okay, so now I've made it double. So you say double. Okay, don't let go. It's going to hurt even more now. So now we've got, you'll notice it's much closer. There's shorter distances, but I also don't have as much wiggle room. I can't move around as much. Make sense? Triple bond. Okay, put your finger in there. Okay, don't. All right, now I can barely move at all. I mean, we are really jammed tight together. Triple bonds are the tightest of the bonds. Okay, now you can let go. Okay, good. Tightest of the bonds, and they are the strongest of the bonds. Have you guys seen, back in the day, people used to have newspapers delivered to their house instead of digitally. Crazy, right? Have you guys ever seen a newspaper get delivered? Yes. Okay. Have you seen people throwing newspapers into other people's yards? Yes. Okay, so it's not just like into a mailbox, it's like hurling it. Those newspapers are usually held by a rubber band. Now, a single rubber band doesn't hold the Sunday edition of the newspaper very well. So what do? They double it up. Because doubling it, double bonds, doubling the strength of the rubber band, it's going to be much, much tighter. It's going to be much stronger. All right, so of these, which is the strongest? That N2. And then, of course, these single bonds are going to be the ones that have the most leeway, the most give, the most room to move. Let me ask you, how many electrons are being shared here? 4. How many pairs of electrons are being shared here? Good. How many electrons? How many electrons are being shared right there? 2. You got to look at what the question's actually asking. I'm not going to be mean and like try and screw you up with it, but I will put questions on there, and honestly, I don't know how I'll ask the question. Whether I'll ask as how many pairs of electrons, or will I ask as how many electrons? It really is whatever my mood is that morning. I'm not doing it to screw you up. I'm just trying to get it done immediately before class. Something to note is that it's really easy to get lost looking at these molecular shapes as flat images. H2O as sort of that L shape. You have to remember, and it's always got to be in the back of your mind, that molecules are 3-dimensional. So here we've got deoxyribonucleic acid, DNA. If you looked at it flat, it would look like this. Actually, that's actually pretty good how it would look. Look like my awesome ability to draw the molecule of DNA. So it looks sort of like that. You don't see the detail that you would see in this 3-dimensional structure. For instance, this, it can look like a ladder. You've got rungs. But this looks like a ladder that's twisted. And the ladder that's twisted has this minor groove here and this major groove there. Other molecules can fit into those spaces, and they can react with it. And when they do that, they can change the shape even more. Form always determines function. Here you have a molecule of hemoglobin. It carries oxygen. It looks like it's got this little hole here. Well, what can fit in that hole? few oxygen molecules. It's like a little Easter basket of oxygen. I have no idea why I threw a periodic table in here. Yeah, it was just in case, so I didn't have to keep flicking back and forth. Get rid of all this stuff that's in the middle of the board now. So yeah, so I can have it to erase. There we go, so we can see the screen again. Yeah. So we covered covalent bonds where atoms will share electrons. One special type of covalent bond is the polar covalent bonds. And we talked a little bit about this in lab. Polar covalent bonds form between atoms with differing electronegativity. Electronegativity is the ability of an atom to attract electrons in a bond with another atom. They suck electrons toward themselves. Oxygen is the most electronegative element that we are going to study. It's not the most electronegative substance, but it's the most electronegative element we're going to study. Oxygen pulls electrons to it like crazy. It is highly, highly reactive in that way. So here we've got this oxygen, very, very, very electronegative. These hydrogen that are less so. Oxygen will pull the electrons from that hydrogen toward it, making the end toward the oxygen very negative, and the other side, where you've got the two exposed nuclei of hydrogen, are very positive. Ping pong balls are great props. So here you go, Gabby. For you, good. You're hydrogen, by the way. You got your one electron. How many more electrons do you want? One more. That's right. And you? One more. I am oxygen, so I've got 6 electrons in my valence shell. So I'm going to put 4 in my pocket. 4. Now, we can share. Okay, hold my hand. It's okay. I'll hold your hand too. We're sharing. Now you're stable. You got 2. You're stable. You got 2. And I'm stable. I got 8. But the deal is, I will suck these toward me like this. Good. I'm not knocking anything over. Suck them toward me like this. So now I've got everything over here. I am more negatively charged. They've got these exposed nuclei over there. Apparently, I'm pointing with my foot now. Got it. They've got these exposed nuclei, so they're very positively charged. I'm very negatively charged. So that is a polar bond. We have poles. The Earth has poles. It's got a North Pole and a South Pole. Where does Santa live? North Pole. Well, you had to think about it for a second, didn't you? Like, is it the North or the South? North Pole Santa, South Pole penguins. And that's important to remember, apparently. Let's see, what else has poles? Magnets have poles. You got a north and a south to a magnet. If you're to hold them toward each other, some will attract and some will repel. Lots of things have poles to them. Some people have poles to them. They've got an upside and a downside, a positive side and a negative side. Now, between polar molecules, you can form hydrogen bonds. Hydrogen bonds will form between any molecules with differing electronegativities in the elements. Here we've got a very positive charged hydrogen. Here's that very negatively charged oxygen in a different water molecule. So these two water molecules will be attracted toward each other. And that's going to come into play pretty heavily when we talk about water. So those are hydrogen bonds. They are intermolecular forces rather than intramolecular forces within a molecule. If you've got serious differences in electronegativity, or you're just not going to, you're going to need to form bonds through just giving up or taking in an electron, you're going to make ionic bonds. So ionic bonds tend to happen between molecules that need to either gain 7 electrons. They're not going to share 7 electrons with anything. I mean, you guys have friends, I assume. When you go to share things with your friends, you don't give them like most of the stuff. You're like, you can have some of it. You're sharing your food. Okay, you go to Chick-fil-A. Yeah. Okay, you go to Chick-fil-A and you go with that friend who totally has no money and is bumming off of you, and you know they're going to bum it off of you. So what do? You go there, you get your food, and you give them some fries. And that's it. They're like, hey, that sandwich sure looks good. And you're like, yes, it is. And you continue to eat it slowly in front of them. Sometimes it's easier just to utterly give something up in order to get where you're going. That person who's going to Chick-fil-A with you, they didn't really have to go to Chick-fil-A with you. They could have just stayed home. I know. You haven't. Okay. From now on, that's exactly the example I'll use. If you have an 8-piece nugget, you're not going to give somebody else 7 of those nuggets, unless you're like their parent, and then it's only because you have to. So here we've got 2 atoms. You got sodium. You got chlorine. Sodium has how many electrons in its valence shell? 1. How many does it need? 7. It needs those 7 nuggets. Chlorine. How many does it have? 7. How many does it need? 1. So yeah, it's amazing, right? So sodium could snatch it, or in order to be stable, sodium's just like, I just don't need this. I'm done with this. You gave me 1 nugget. That's not going to do a thing for me. I'm not going to have anything. Throws it away. So here's. So once it throws it away, how many electrons are in its valence shell? 8. Now it's stable. But poor chlorine sitting over here, it's got 1 empty. What can it do? Well, suddenly there's an electron hanging out in the environment. Chlorine's like, I will take it. I will eat that chicken nugget off the floor. Now I have my 8. Chlorine's pretty nasty. Chlorine kills most things, so it works out. Here, take this. Check this out. So you've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. You suck at this game. Here's another one. Okay, good. How many do you have in your valence shell? I suck at this game too. All right, you got 1. How many more do you need? 7. 7 nuggets. I could give you these, but I'm not because I'm selfish. Instead, you just throw that one. And it comes right back to you. Awesome. And now, underneath that, you happen to have a whole bunch. So now you're totally stable and life is good. Hold on to those. Mainly because I don't want to hold on to them. You have 2 kinds of ions. I'll take them back. Do this whole kangaroo pouch thing. Oh, lost my microphone. Put that back on. And I shouldn't be trusted, or you shouldn't be trusted? There you go. No, okay, you're right. There we go. Lots of them. All right, so you got 2 big kinds of ions. You've got cations and anions. An anion is negatively charged. If it's negatively charged, it has too many or too few electrons. Too many. It's got too many electrons, it's negatively charged. If it's a cation, it is positively charged because it's got fewer electrons. This is how you can remember it. There's a few ways. Okay, so any ionic bonds form when a cation interacts with an anion. So if you were to have, the way I remember is cats. How many of you guys like cats? All right, the 4 of you. If you like cats, cats are a positive link, so they're positively charged, right? If you don't like cats, I don't know, running over cats, it's a positive thing, whatever. Anions, they're like onions, right? Onions give you a bad breath, and that's a negative thing. Don't do that on a date. So, sidebar. Second date I went on with my wife. Before she was my wife. I had gone to Outback the night before. And you go to Outback, you've got to get a bloomin' onion. And I ate that. And then I was like, oh, now I've got a date. So the next day I woke up and I brushed my teeth and I could still taste onion. And I could still smell onion. So what I do, I brushed my teeth again, probably like 15, 20 times in about 2 hours. Didn't help. So I had to go to the store and I got those Listerine strips? Yeah, downed a package of those. That didn't work. I tried everything I possibly could until by the end I had very minty breath that smelled like mint onions. And I was so close to canceling that date because like this is going to be so embarrassing. Turns out it didn't matter in the end because we sat far apart, and that worked out for me. I want to ask how long you made that. How long ago was that? 15 years? Yeah, these are things that you remember forever and ever. Another periodic table, just in case. Can't have enough of those. Oh, there you go. Onions, anions, there's a difference. Do not put onion on your exam when talking about anions. It happens way too often. Anion. Anion. If you understand prefixes and Greek and Latin roots. Ionic bonds, these between cations and anions, are very, very easily broken down in water. And water, of course, is the principal environment of the cell. So we've got covalent bonds, super strong, by sharing electrons. Ionic bonds, giving up or taking in electrons. And then hydrogen bonds are between molecules of different electronegativity, with elements of different electronegativity, and they're intermolecular forces. Now, last thing I want to talk about with this section, then we'll move on to water. And I'll give you guys a quick break because I know you're probably, I've seen you guys looking at the clock. I have been too. You've probably heard of these things called free radicals. You hear about them a lot in commercials. People are always talking about it will stop free radicals, or free radicals are implicated in this, that, and the other. Free radicals are implicated in aging, cancer, heart attack, atherosclerosis, trauma, hyperoxia, stroke, cataractogenesis, retinal damage, liver injury, sexual dysfunction, periodontitis, vasospasms, dermatitis, asthma. I mean, you name it, free radicals are involved. Of course, I totally stole that from an advertisement. Yeah, no, it was on this bottle of, I think it was like blueberry juice. And they're like, this has free radicals in it. And if you drink it, you'll be protected by the free radicals. Now, here's the no, from the free radicals. Sorry. Unstable ions are called, if they're completely unstable, with very, very high electronegativity. That is, they pull electrons like crazy. They're going to be termed free radicals. So if we were to do this, let's go with these electrons. Yeah, Arthur, here. You hold this. You hold this. You hold this. And you don't get one. All right, so here's the, okay, you can have this. All right, so here I am, a free radical. I am extremely electronegative. That means that I pull electrons to me, right? So here's that. So I come along and I'm like, oh, I'm bigger and stronger than you. I stole your electron. Now I'm kind of stable and cool, but you are totally unstable. You're angry that you lost your electron. You can't take it back from me. I'm stronger than you, but she's not. So you steal her. Yeah, no, he's bigger and stronger. It's okay. But here's the deal, though. So he's now changed his shape. That electron doesn't go back where it started. It's in a new place entirely. Different form, different function. Well, now you're unstable. So what do? You can't take it from, that's right. So now you've changed your shape. And you go ahead and steal Arthur's. And then you're dead. This is what happens in bacteria. What do you use hydrogen peroxide for? Cleaning things, cleaning wounds, right? So you're bleaching hair, thanks. So if you were to take this hydrogen peroxide, this free radical, put it on a wound, it will find the bacterial cells. And it will start stealing electrons from the molecules in the bacteria, changing their shape, changing their form, changing their function. And if their form and function change, the bacteria likely can't survive. It's kind of cool. That's what free radicals do. And they can mess up a lot of different things. This hydrogen peroxide, though, doesn't really hurt your cells when it puts it on. You put it on, what happens to the wound? It bubbles, because your cells are fighting back. Your cells actually have an immune response, not an immune response, but a response to the hydrogen peroxide. Inside your cells, you have these little things called peroxisomes. And those peroxisomes break down hydrogen peroxide, releasing oxygen. So as your cells are working, You use this poison on the bacteria, but you had the antidote. You're converting it all back into pure oxygen. So the antioxidants counter the effects of free radicals. They can donate electrons freely. So it's sort of like, here, May. Here, you get that one. All right, so here's how this one works. If you've got some antioxidants, vitamin C, vitamin E, drink some orange juice, whatever. Here, that's yours. As Gabby, you get to be the antioxidant. There you go. So Gabby's the antioxidant. Here I come, the free radical. I'm all like, I'm going to steal this electron. But Gabby, she doesn't need her electron. She just like throws it at me. Oh, an electron going across the floor. I better get it. Now I'm stable. I don't steal yours. I don't steal yours. And the chain reaction doesn't happen because we had this molecule over here that donated the electron. Nobody has to die. Everybody gets along well. For some reason, and I don't know why this always sticks, but I always think of antioxidants as the Easter bunny of the cell. They just go around like handing off electrons, and I always imagine them skipping, even though they are molecules that have absolutely no limbs. That's how my head works. Okay, so any questions on basic, super basic chemistry? If not, once we've gone from subatomic particles, protons, neutrons, electrons, we've built them into entire atoms. We've taken those atoms, we've combined them together to form molecules, and those molecules can interact in different ways. The way molecules interact is in chemical reactions, where one or more substance is changed into another. On the left side, you'll have your reactants. On the right side, you'll have your products. The little arrow means it's moving in this direction. Now, all chemical reactions are going to require energy. We'll talk about that later in the course. We've got a lot to talk about with energy. In living organisms, most will require a catalyst, something that will speed up that reaction, like an enzyme. They're going to proceed in a certain direction until they reach equilibrium, until both sides equal the amount of products being created are the same as the amount of products being destroyed. And most of these reactions involve reactants and products that are dissolved in water. Water is key and crucial to chemical reactions for biology. Most of your body is made of water, and all the chemicals in your body are dissolved in water. And if they're not dissolved in water, your body is trying as hard as it possibly can to get them out of your body in the most efficient form it can. And that's where we're going to start moving into the properties of water. Any questions thus far? Life's good? Huh, look at that. I stuck a bunch of random content review questions right into the middle of the lecture. So if you get to the end of this lecture, make sure not to forget these, because these are really, really important, especially the stuff about electronegativity, chemical bonding, like really, 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 really important. I should do a review section. I do that. I have to do one. And I believe it's tonight. I should do a review on the test? I didn't intend on recording a review session. I would come if I could, but I can't. Well, here, I'll stop this.